So yeah, hello, good day everybody. So today is the second study group session. Staying in the theme of high-level overviews, we're taking another look from the Starkware group. This time it's Michael Ryabzev. I hope I say that correctly. This is a recent talk he gave in October, and specifically it was about a Fibonacci example, and it started to dip into the mathematics around how to construct Starks. What does it mean to have completeness and soundness as you're building these zero knowledge proofs. So a bit of a preamble that he started with. Again, you have two sides in this zero knowledge setup. You're going to have the prover who claims knowledge of a secret, and a verifier who is skeptical about the prover and wants to have a strong proof such that they are satisfied. An example that was led off with is, okay, the prover wants to make a claim that they're possessing greater than 100 Bitcoin. The verifier, in a malicious case, maybe wants to learn which Bitcoin addresses, or wants to learn something about the total amount or possibly the keys of those Bitcoin addresses. And so the prover is going to be able to make a zero knowledge proof such that addresses, keys, total amount of Bitcoin remain secret, but the verifier is satisfied that the prover does in fact possess more than 100 Bitcoin. So overall properties of zk Stark is that the verification is a logarithmic time, which as Michael Mikhail pointed out, that means it's practically a constant time as as the Stark circuit is getting bigger, and you have the efficient proving time because it's close to naive execution. It's quasi-linear. All right, so the main part of this talk and of the session today is going through a construction example of the Fibonacci sequence. So the statement or the claim that the prover will make is that they know two secret numbers, A and B. Those will be the starting values of the Fibonacci sequence for some sequence length. And so the constraint then is that you have an A sub I added to an A sub I1, and that will be the next value. And so we're going to build this up over a number of trial rounds, starting from naive and ending in zero knowledge. So the naive is exactly what you might expect, which is the prover is sending A and B explicitly. And so the statement is just, I know secret numbers, and the fifth element is 42. So A and B, which are my secrets, are 12 and 6. The verifier is just going to compute up to the fifth element. You're not getting anything out of this. So how to do better? This is where you're introducing the third party, so you don't just have the prover and verifier. Eventually the notary will be a cryptographic method. Especially the statement is that you want the notary to be the only trusted party, because both the prover and the verifier have reasons to cheat. The prover might want to lie about the secret, and the verifier might want to learn about the secret. So in the second trial, where we've added this third-party notary, the prover is passing the notary the full Fibonacci sequence. So if we have a range of 5 values, then there will be a sequence of 5 values that the notary then has. The verifier is going to ask for a sample of 3 consecutive values, and then they can verify that with those 3 values, that the constraint of Fibonacci is correct. You start to, so the problem then is that the soundness is very weak, because this is only a probabilistic check. The verifier is sampling some cells and testing that the constraint holds. So when you change the length of the sequence from 1 million to 5, verifier then is only reading a very small number of cells. And so soundness here is the problem, because even one wrong number in the sequence would change the overall outcome, but you wouldn't notice that unless you were lucky and selected, lucky in the sense of the verifier having selected exactly where one of the values was changed. So if you move from a sequence of length 5 to a length million, then this starts to be, a very big problem, because the prover could inject a bad value anywhere. So how to fix this? Well, you start to add some maths. In particular, it's algebras, it's polynomials. So effectively, it's at a high school level of algebra. And so the overall idea is that given a polynomial of p of x, so x is one of the values in the range that the prover has proved, you're going to have a polynomial such that you have a p of x equal to an a of x with x minus 1 polynomial as well. So you get this a of x if and only if the polynomial at n is equal to 0. So this is a vanishing point. It's also meaning that n is a root of p, which just means that it's 0. And this, you also have the opposite being true, that n is a root of p if and only if p is factored in such a way that p of x is divisible by x minus n. The second, core point is that you have interpolation. So this means that when you have d plus 1 points, so the degree of the polynomial plus 1, and you have points x at I, y at I, there's only one polynomial of degree d that's passing through all the points. So the base case there is that if you have 2 points, there exists only one line that passes through both points. So with this simple theorem, you can extrapolate it to higher degrees of polynomials. And basically that's basically that's it for the rest of this example. Those two ideas. So heading into the third trial with the intention to increase soundness, what changes is that the prover is finding a low degree polynomial, which is encoding the Fibonacci sequence. And so no longer is the prover sending the full sequence of Fibonacci numbers to the notary. Instead, it's just passing this polynomial function that it has found. Say again?
So there is a polynomial that can represent the Fibonacci sequence?
So the encoding is that,
I think you just mean the first n numbers of the Fibonacci sequence, right? Because Fibonacci sequence in itself would be infinite.
Right.
And then that cannot be a polynomial.
Sorry, yes, you are correct. Yeah, the polynomial being defined is for the starting point in the range. This is the encoding. You are correct. Yeah, exactly. And so the verifier then is being allowed to query this polynomial f of x at most 3 times. I think the most important thing here is that the number of times the verifier is allowed to query is less than the degree of the polynomial. And what's changed, or the other important point here, is that the verifier is querying outside of the sequence that the prover the prover was making the proof of. So when we said it's a range of 5, the values sampled are outside of that range of 5. So we're increasing soundness, and the problem is then the sequence of values is not what the notary has. So the verifier wants to the verifier wants to be satisfied or convinced that by only sampling 3 values of f of x, that the proof is in fact correct. And so the verifier is going to request a witness, which is attesting that this polynomial f of x is valid. So the verifier notices that f of x is valid if and only if, by walking through the range, you end up at the point where all these 3 parts are 0, of course, and that the final value that was stated is also equal to the final part of the range. All right.
Yep.
And so at this point, Mikhail was saying, building this up and saying exactly this a more general statement exists, and in general, this is why a low degree polynomial testing, I guess, is quite efficient because you can just have a small number of constraints when the degree, like when the polynomial degree stays low. It was my takeaway. I could be wrong there, but this is what I'm kind of remembering from that problem statement. And so here's where we start to construct or start to add in a number of other kind of building blocks, if you will. So the verifier will define the imaginary polynomial q of x such that q of x is the f of x and x plus 1 minus f of x plus 2, which is following the first part of the problem statement.
What do you mean with imaginary polynomial?
So the verifier is imagining q of x. The reason is because
it's nothing to do with imaginary numbers.
No.
No, it doesn't.
So the reason that it's an imaginary polynomial is because the verifier was not allowed to sample in the range that the prover made a sequence of. So every time we see x in these equations, those are the real, those are values in the range that the prover has, but the verifier was only allowed to sample outside of that range. So this is why the verifier does not know the values with f of x. So continuing with kind of this polynomial math, q is vanishing when q is 1, 2, or 3, which are the three draws that the verifier gets. It gets to take 3 values out. And this is holding if and only if f of x is describing a valid Fibonacci sequence, because this is a property of that sequence. And so additionally, yeah, we're saying that q of 1 is 0 if and only if q of x is divisible by x minus 1. And the same for the second and the third draws where x minus 2 and x is minus 3. So these are all zeros. These are all roots of the f of x polynomial. So what you can then say is that there exists z of x that is equal to x minus 1, x minus 2, x minus 3, because each of these are zeros as well. So z of x then will also be a 0, and we then have this imaginary q of x. So this imaginary q of x, which we started with, it's a linear combination of the f of x, which is a degree 4 polynomial. Q of x is also degree 4. Yeah, just to be said, adding two polynomials together, they stay the same degree. However, z of x is a polynomial of degree 3 because the verifier was only getting to draw 3 times. So the next important statement is saying then that f of x is valid if and only if the ratio q of x and divided by z of x is a polynomial of degree 1. Another way to say that is that there's a ratio since q of x is divisible by z of x. We're going to call this ratio b of x. So b of x is equal to exactly this. And now b of x is going to be the witness statement that f of x is describing a valid Fibonacci sequence. And if you rearrange this and you move z to the other side, then we now can say that q of x, which is the polynomial that the verifier was imagining, right? That it's going to be equal to the ratio, which is the witness, multiplied by the z of x. Okay, so this was the baseline. This is the setup, and this is the part then that will allow a verifier to be satisfied of a proof. So the test becomes then the verifier will choose random values outside of the range. So in our case, the range was 5, so r is greater than 5. Then the verifier is asking the notary to draw 3 values for this r. So r plus 1, r plus 2. The notary will give back these values, and the verifier can now make a test that, b of b of r by z of r is equal to q of r. And remember that we're in Fibonacci, so we can see that q of r will be equal to the f of r plus 1 minus f of r plus 2, right? Because we know that we can vanish there, we can get to 0 there. Okay, so now what can we say about the completeness of this proof? The idea is that the idea overall is that the completeness of a proof system is that a property of the statement we have made is that the claim will be correct when the prover can always generate a proof that will satisfy the verifier. So using only these statements, they must hold true for all the values that the verifier might draw on. So what that will lead us to is saying that f of x is valid when b of x is constructed by b of x is q of x over z of x, and then the verifier must be satisfied. So this is important. We do have completeness at this point. However, we're missing soundness, and soundness is the ability of the prover to cheat. Specifically, it's the probability that the prover can again inject a value there. So we need to do some additional work. Assuming that the f of x is not valid, then there cannot exist a b of x. Why? Because when we look at the statement that we made, so we have the imaginary polynomial that was that the verifier was imagining, and then built up a statement so that b of x times z of x is equivalent to it. They have to stay. I mean, if the prover really wanted to cheat, then it has to stay as a degree 4 polynomial. However, they're going to be different when the prover is cheating. What this means is that at most only 4 points, which are the 4 roots that the polynomial could share, will be the same. So when this is the case, there's only 4 possible values then that would satisfy the equation. And if the verifier is drawing at this r value from a range of 1,000, so 1,000 to 2,000 because it's greater than 5. When they're drawing in a range of 1,000, then the probability of the verifier being able to cheat is at most 4 over 1,000. So for me, this I guess this kind of intuitively made a lot of sense. I had to rewatch this part of the talk a couple times. Does anybody have questions on that? Silence means no. Okay.
No, I mean I do. I was also confused a bit about that because he talks about Shamir secret sharing and hiding a secret in f of 0 and have the rest of the values of the function f1 and f of 2 being random.
Right.
And kind of extending the degrees of the polynomial to 8 instead of 4.
Right.
So maybe that comes right after this, right?
It does, yeah.
Okay. Then this is the Shamir secret sharing part that I'm not entirely comfortable with.
Okay. Yeah, I think this builds up on it because this is without hiding values in the polynomial. This is just saying that when you have these 2 polynomials, they can only share 4 points. So the probability of the prover being able to cheat goes down dramatically, which is great because we don't want that, right? We want the proof to be sound.
And so a verifier would cheat by submitting a polynomial that has at least one similar point. Is that it?
Yeah, I think the idea is that when you have the 2 sides of the equation, right? This is the proof part, and this is the the quote unquote imaginary part. But they both need to be degree 4 polynomials because you want to be able to have q of x over z of x be a degree 1 polynomial. So that means they must be degree 4. And these 0 points, right? Like when you're drawing parabolas, when they cross over. Like, so yeah, this is just like I don't know. I had to remember this also from my high school maths, but it just means that they can only match exactly on 4 points. If you were to plug in the 0 points, then yeah, you get 0. Otherwise, you're somewhere else in that XY coordinate space. So the resulting value would not be equivalent, and so this test would fail.
Okay. Question. We talk about the cheating of the prover, not of the verifier, right? I have to admit that I haven't seen the video, but Alex, you said that cheating of the verifier, you probably meant cheating of the prover, right?
Yes, sorry, I meant cheating of the prover.
Right. Right. Okay. So great. So we have a much better property here, and then so it's just to be so there was a bit of a discussion that happened in the talk at this point, and somebody was asking, how is it that you're encoding a program? And this was interesting. I think that when you're using Starks to encode a program, we're saying that the degree is linear with a number of registers in the program. So literally assembly style where you're plugging in values, and then throughout the talk it's saying Starks are using low degree polynomials. So what does that mean? It means it's bounded. So if you had a 1,000,000 degree polynomial because you had 1,000,000 registers through the program trace, then it's bounded. It's not going to blow up at some point. If it's a 1,000,000 degree polynomial, you have anything between 0 and that. Yeah, like so. Anyways, it's just bounded. It's inside of the range of that polynomial. I didn't quite understand the part where he was saying you can choose the domain of a query to be of much larger size than the program trace. He was I don't know. It effectively sounded like something of this statement as well. I don't know if anybody had a better grasp of that.
Well, you work over finite fields, so we can just blow up your finite field which will be much larger, have much larger number of elements than any polynomial you would practically imagine. So even if you work in the field of in a binary 2 in the power of 64, still much above a million. So in principle, your soundness is not that effective.
Okay.
Where does this number 1,000,000 degree polynomial comes from?
I think he was using.
It's just arbitrary. It's just some number.
It must be bounded because the Starks is built on bound to incompleteness or something like this, right?
So Starks can only be used for bounded computations.
Yeah, and you have to specify the bound in the beginning, right? Everything is then with respect to the bound.
Well, in the first place, the verifier and the prover, they agree on the nature of computations, so they in principle have the construction. So they both know what would be the highest degree polynomial, and after this, in principle, they can choose the field over which they will work, maybe just to increase the soundness, for example.
Okay. Great. So with all of this being said about the soundness, we still don't have zero knowledge yet with the different setups that we've had. And the reason is because if the verifier can read some value, it's still changing deterministically based on the secret that the prover was choosing. So we then move into the final trial. I guess this was interesting for me. I didn't have a good technical understanding of Shamir secret sharing, and the fact that it's technically this, but somehow extended, I guess made me feel a little more comfortable because I have an idea of how it works, even if I haven't worked through the math once before. And it was said that the underlying concept here is that you can hide secrets in the polynomial, and this is because when f of x is a degree of d, then when you only know a few of the f of x values, for example, we have a range of 5, so there's 5 f of x values that are being included in the proof. You don't necessarily know you don't know anything about the rest of that polynomial. So the example used in the talk was that when you know, for example, the 0 points if you only know like 2 points on a parabola, you would know nothing about a third point or any other point, in fact. You don't even know where the parabola crosses the y-axis if you have points that were not crossing the y-axis. And so the principle there, or the core concept there, is that you can hide a secret in the zeros, which I don't really have a good grasp of, either mathematically or as like a mental picture. If anybody else could explain that better, that would be nice.
I think I can think about this a bit and then maybe explain it next time, or someone else has a good idea.
Well, in principle, this is not that difficult. I don't remember the exact rationale why it's a constant term of the polynomial is used. I think mainly because it's very easy to calculate if you know if you know enough numbers, like enough values of the polynomial at different points. You can much easier calculate zero value than some arbitrary coefficient. You still can calculate the coefficient, but it's much easier to calculate the zero term. But in principle, if your polynomial is of degree n, then knowing any n plus 1 distinct values allows you to uniquely reconstruct the polynomial. So you share the way that you just need values from different people. Well, you make the polynomial and use the secret as a constant term. So you make a random polynomial with just constant term somewhere. You evaluate it at some points and give these values to different participants. So if n plus 1 participants get together and share their numbers, they can reconstruct the polynomial and get and recalculate the constant term in this case. But this is, well, this secret sharing is just high school algebra in principle. If you know n plus 1 points on polynomial of degree n, then you can reconstruct, and this reconstruction is unique.
Right. Okay. Okay. Yeah. So then, okay. So we're basically at the ending, but this was the secret, is using Shamir's secret sharing. So effectively, when you do not have enough points, that the number of points you have is less than the degree of the polynomial, then yeah, you're not going to be able to discover the secret, or discover, I guess, the f of 0, one of the roots. So when you have this range of 5 values, so f of 1 up to f of n, which was the chosen sequence in the proof, then we should do the same as Shamir and just add some random elements into the sequence before doing the interpolation, which results in the polynomial that is sent to this notary actor. So what that means is we have the range f of 1 to f of 5, all of those values, plus you draw some random, you draw some random values, and then you extend the range. Let's say we extend it up to f of 9. So we now went from degree 4 to degree 8 polynomial, and this doesn't change the way that the verifier will do its baseline setup or anything else. The reason is because the elements that were in the sequence of 5, they were not known to the verifier. It was not allowed to draw from that range. R had to be greater than 5, and now it doesn't matter that there was a degree 8. It's still going to have to draw over that. And so the one thing that does change is that with degree 8, when we take this range of 1,000, the probability of cheating has changed from 4 over 1,000 to 8 over 1,000, but this is still quite small. And yeah, so just to say that the f of x, which is the interpolated polynomial that's sent to the notary, is defined different. The b of x, of course, would also be different because q of x is a ratio of it in the construction that we are doing in this baseline. What I called baseline. And so the interesting part, or the really great property, is that the execution of the protocol results in the same soundness of before, and we now have no leaking of secrets. So we've arrived at a zero knowledge proof. And then there was a long discussion at the end of the video. I think there was some interesting parts there, but I stopped my note taking as he was wrapping up on the final slide. And so the takeaways that Mikhail wanted the group to have was that, yeah, completeness is that any correct statement will have a valid proof. The soundness of the proof system is that there's no valid proof for any incorrect statements. Fantastic. ZK proofs are requiring randomness. This is because we're choosing some random points to extend the sequence with, I presume. And then that the polynomials are being used and they're useful for zero knowledge and to have soundness of the proof system. And that was it. Those are the notes I had.
Awesome.
So what questions or what kind of further things come to mind for you guys?
This was, because I was coming late into the talk here, this was about the video about the Fibonacci sequence, right?
Correct.
It was linked, but it was in Starks. I was under the impression that it was about Aurora.
So we're still in this idea of intro topics. I'm not sure if it's Aurora, when I'm very honest. I haven't looked closely at this.
Okay. But it's in the beginning you said that you built these air constructions, so no one constraint system. So it's probably Starks. It is.
So it is Starks. The deepest level here is just that there is a constraint system, and so this is how the verifier will know what to do, because the verifier notices that the polynomial which is submitted to to this notary reactor, right? The interpolation that the prover has done is f of x, and the verifier knows that, all right, these should hold true, because there's a range of 5, and that fifth element must match what was that? Yeah, the fifth element must also go to 0 when you complete these steps. So that was the entire constraints.
Do you think that the talk or the video was deep enough so that you are now able to build something like this for yourself, let's say on a different recursive sequence?
So honestly, for me, with pen and paper, I think yes. When I can, when I can do this, when I can do this, I think I'd be able to get there. I don't think I'd be very fast at it though. Also, there's supposed to be a more. He kind of teased it that there's supposed to be a more general statement. So I would like to know what that is when I'm honest. Maybe have you been reading the Aurora paper, Mirko?
What would you like to know?
I would like to know what the more general statement is. That this is exactly Fibonacci sequence, and Mikhail was saying there's a more general statement existing, and this is what's used in Starks to solve these constraints. So instead of, because I guess this is a limitation of at a very high level, maybe this is wrong even, but that you need to construct a new circuit every time for ZK snark. And this is maybe because you have to do this encoding directly, but Stark is supposed to have a more general, way to make these statements. I mean, sure, you must end up with specific constraints, but I thought that there was a way to give it a problem domain, and it would be not per problem, if you will. Or am I off base there?
I think this is, well, maybe it was misunderstood, but in principle, any bounded computation is more or less uniquely represented as a set of machine registers, which can be used for error reduction. In principle, your error constraint system will be unique per every program. Okay. Well, most likely it's going to be this. I mean, error constraint system is very nice and good and easy and everything, but I think it should be unique.
So if you have a register representation of a computer program, then it's more or less easy to make an error out of it?
Yeah, in principle, your error is basically a tape which which just records state of every register which is used in the machine without an external memory, and you just makes a low degree polynomial which gives you a connection between every next register state.
Okay, it's very cool. So if I'm able to write my ordinary computer program, let's say in register code, then I can easily convert it to an error. So you know what I mean?
Yeah, in principle you do. Just say that any computer program is non-trivial because memory management is difficult.
Okay.
And this is the same for snarks and for starks. Having encoding the access to external memory is not trivial. And this is the last part of the original Stark paper, how they solve the external memory read and write problem.
Yeah, okay, I see. But if I'm good, let's say, in writing assembly programs that only uses my computer registers, then and it's more or less easy to convert them to errors if I have no.
It's more or less the same as Tiny RAM compiler does, except Tiny RAM works with external memory. But yeah, in principle, you can even write a compiler. It may be not as efficient, but in principle, it's possible.
Cool. That's really cool.
Okay. So for me, I guess this was nice to start heading deeper into the weeds, if you will. I think for at least to say it out loud once to the group, my end game, or at least the first checkpoint that I'm hoping to get to, is to be able to build a circuit and to have an understanding, not just to use a tool. And then deploy that, or it doesn't even need to be deployed, just to be able to run it on my laptop. So at some point, maybe in one month, let's say 2 months, I would like to maybe have a session on like a software library to do this using, I don't know, possibly Billman or something else. But I think we still have more maths to get to, and it seems like on this call especially, some of you have a pretty good understanding. Does anybody have recommendations on other, let's say fundamental maths that we need, or possibly some other examples that they work through, papers or appendixes of those?
I think the 2 videos that Eli shared of his own lectures at Technion Cybersecurity Summer School, where he goes through, I think one talk is about arithmetization,
right,
and there's a second one, and I think these are pretty deep into the maths as well, and go over maybe some of the stuff that we've seen, but also extra stuff. And I think it might be useful in terms of getting a more introduction to the maths, maybe a bit deeper than what we've looked at so far, but still I think it's a logical step forward.
Okay.
But what kind of mathematics do you actually need? I mean, it's more or less just prime field arithmetic and basic stuff about polynomials, right?
Yeah. No, I think what Matthew meant is more kind of like putting the maths in context with the technology, and kind of where it fits in, and understanding the nuances within it, rather than just like learning algebra, because again, like polynomials or even just prime field or field theory is relatively simple to understand if you just look at, I don't know, an algebra textbook or something.
Well, the most interesting and difficult part is because this construction in principle works, but it will give you enormous size proofs if you just use it naively, the same way as every representation is constructed naively. So the next step is the Frey reduction, which I think done not over the registers, but over the like if you imagine the tape as a table with column and rows, where each row is a set of registers at time t, and each column is the state of some register at times from 0 to end of the program. And initially, what we do right now is we more or less characterize a polynomial which binds two full register states
Right.
in two different times. But the Frye reduction, I think it works over the columns, which makes it much more efficient. The same way as reduction from rank 1 constraint system to co-ops makes snarks quite efficient. So I think this is going to be the most difficult part. I personally didn't get to it yet. I have a practical problem with snarks right now, which I have to write. Implement. But this is a point which I don't yet know, and I think is going to be most interesting and difficult. And this is actually what makes starks efficient.
How do you say that? It's Fries, as in FRIE, or?
The fast Reed-Solomon.
Uh-huh.
I don't remember how it's. This is a proximity proofs that you're like two encodings of two elements are close if and only if your elements which you encode are close. In principle, what you do is you encode polynomials, I think. Something like this.
That does sound very fun. And interesting and tough.
Yeah, because it's the same way as with the snarks. Rating rank 1 constraint system is more or less okay, can be easily done. Reduction to co-op takes a lot of time, but it's still doable. But here, I think the reduction to the next step is much more difficult.
Okay. Nice.
What is the next step after quads?
In snarks, the step after co-ops is directly the proof system. I mean the polynomial division and in principle. After co-ops, you use one of the proof systems, either the Gross or Pinocchio. And here, after the air representation, you go directly into the starks.
Nice. I guess out of curiosity, you say that you're working on something now. Is any of that going to be open source, or are you leveraging some open source stuff?
No. I'm just rewriting Belmont for Ethereum.
Okay.
Yeah, I should release maybe next week if I'm in time before the ETH Singapore.
Okay. Yeah. Release it when it's ready. Conference-driven development doesn't work so well.
Almost everything works. Some parts should be extended.
Okay.
I have a more general question. This is now focusing a lot on starks, not on Aurora. Are there any special reasons for this? Because personally, I haven't decided yet. Should I focus on Aurora or on starks? My ultimate goal is to have some kind of recursive system, like the Coda blockchain, and so I'm not entirely sure which road to go right now.
So I could answer your question first with another question. What is the difference, or why is it that you're drawing a line in the sand between Stark and Aurora?
I think Aurora is building on constraint systems like snarks, and Stark is building on the air system, right? It's pretty different. I'm not entirely sure because I haven't looked deep into it yet, but I think the setup is pretty different, right?
I think more or less every program can be represented both ways. I think just every practical problem can be represented in both ways. And I think air can be transformed to rank 1 constraint system if necessary. But in principle, I think it starts with recent advancements in Stark-friendly hash functions on a practical application side may be more useful, because Aurora is much easier to write because error reduction is much easier to write and make automated than rank 1 constraint system. But I mean,
but I thought R1CS was a sub constraint of air. As in one of his talks that Ben Sasson says air is just a more generalized way than R1CS.
Yeah, it's true in principle because rank 1 constraint system is in principle a set of 3 matrices, which when you multiply them gives you efficiently rank 2 constraints. So your constraint over each variable is at maximum quadratic. With air, your constraints over the set of registers over 2 adjacent steps of computation are in principle of degree n, which of degree 2n, where n is a number of registers which you use. So it's in this sense it's more general because it allows you to build higher degree constructions and higher degree constraints. But I think in principle you can take the air and convert it to rank 1 constraint system. It's just a number of constraints will increase.
Yeah, but then the question is how efficient it is still.
Well, the question of efficiency is not your initial constraint system, but how efficiently you can make this improve. And those were different for Aurora and Starks. But I think Starks are much more efficient in terms of computation.
Okay.
I mean, I didn't check it yet personally, but I think they also is more easy verifiable, and people work with Starks in a settings that most likely they will be much easier to verify in a smart contract. But if you build something separate, like completely separate blockchain, you can do anything.
Yeah, Aurora has some better theoretical complexity measures, right? I'm just looking it up. Something is shorter.
Okay. Yeah. So I guess also to answer your question now, Mirko, why are we focusing on Starks and not Aurora or anything else? I think in the beginning, we are still the beginning. It's the second session, but we were kind of brought into this channel to say, okay, let's learn ZK Starks. I think Anna changed the name now to just ZK Study Group, which for me personally I like. I think that there's probably complementary, subsets of each of these approaches, each of these systems. So I don't know that we're focusing only on Stark, and if you want to talk about something else, you better find another group. That's not the point. It was just the first sessions and trying to do something before the holiday time is upon us, meant that, okay, we're doing a high level and we're focusing first on Stark while we build up, kind of a baseline of people who would like to present topics and lead these sessions. So
I think in any case, Aurora and Starks are highly related. Reading quickly through the introduction of the Aurora paper, they do say that Aurora is built. Aurora improve and complements the work on Starks, and that it's just faster.
Yeah, and shorter length.
Yeah, shorter proof lengths, and that ultimately what they use is IOP, interactive oracle proof. So maybe one session that we could do when we feel more comfortable with Starks, which I feel like we're getting to slowly, is to talk about that particular thing, right? Interactive oracle proof, which I think helps explain Aurora, or at least helps understand the difference between normal Starks and what Aurora is doing, or where the efficiency stems from in Aurora.
Yeah. Proof time is also shorter, so this might be interesting for people who want to build a succinct blockchain, I think.
Right. Yeah, that was one of the kind of the jabs, quote unquote jabs, that I heard Eli say in that first talk to Coda, that if the proof time is so long that you're having more blocks advance, then there's not a big difference between proving a block and when the next block arrives, then what are you doing?
Well, if you want, well, first of all, making the blockchain which just uses snarks or starks or whatever to prove the block correctness is quite pointless. Just if you don't have the consensus, because if your prover is efficient, everyone can make blocks, just empty blocks, and just spam the network.
This is something else.
Yeah, this is something else. That's why most of the people work in the settings that they use the Ethereum as a consensus source and use snarks, starks, or whatever to make something practical on top of them. So that's why core as it is, I don't know if it's even necessary without some, well, if they have the consensus mechanism.
Basic idea is to get rid of, let's say you have a Bitcoin blockchain with all the dead transaction in the transaction graph, and you can basically get rid of them and only keep the UTXO set more or less and prove that it's the correct UTXO set. I think that's the overall idea.
This is a confusion in principle. I mean, in a practical setting, the Ethereum state, the amount.
I'm not talking about Ethereum. I'm talking about
it doesn't matter Ethereum or Bitcoin. The largest set of data in there is just for example, Ethereum state is not hundreds of gigabytes; it's just a gigabyte or two. It's the amount of data required for you to take the transaction and execute it on a latest state. So the whole amount of data which is required to just make the next transaction. In Bitcoin, the UTXO set is also small. And everything else that the Bitcoin client keeps is the index and all the blocks which you don't want to remove. In principle, if you introduce the same RSA accumulators or whatever, to sync with the network, you don't need to download every block and apply them to your index. You can just take the accumulator, take a set of UTXOs, and just say, well, this is a accumulator which commits and which is consistent. You can get it from every participant of the network. You can take any form of accumulator and say, okay, this is my accumulator, this is my UTXO set. You can just directly download it, check that they both correspond, check that the accumulator corresponds to the latest value from consensus, and that's it. You can sync using 2 gigabytes of data download.
A lot more general, because also consensus can be changed. Can now talk about blockchains which have no Nakamoto context. I'm just interested in this in theory, to see if it's really probable to get a 16 blockchain.
Well, I mean, if you don't have the consensus some other way, you don't need, well, I mean, you need the consensus first. And basically consensus is the first part which is required to even accept your proof of valid state transition in this block. So without the consensus, all these constructions are quite pointless. And if you have the consensus, you just can use much simpler tricks and snarks and starks to verify, to reduce this amount of data which clients need to keep at the point of time. I mean, in every blockchain, consensus first, everything else is after.
Sounds like a reasonable statement. I don't think I can unpack that further right now. I'm gonna end it here. I'm gonna end the recording here. If we want to keep talking, we can, but just